Okay, so we talked about this in Chem 1. I'm sure most of you do not remember it, but water has the ability to self or auto-ionize, meaning that it will react with another water molecule and form the H3O+, the hydronium, and the hydroxide. Okay, and when it does so, it's actually a very small portion that is doing that, only about 2 billion, 2 in a billion, not 2 billion, 2 in a billion are ionized at any instant. But it may do this self-dissociation, okay? The equilibrium expression here for the auto-ionization is Kw for water, okay? And it is equal to the, just like you go back and look at that equation, we don't include pure water, so the Kw is equal to the hydronium concentration times the hydroxide concentration, and they are equal to 1 times 10 to the negative 14. Technically 1.0008, but we're going to use 1 times 10 to the negative 14 at 25 degrees Celsius. Okay? Remember, K is affected by temperature, so if we change the temperature of the water, then that is a slightly different number. Why 25 degrees Celsius? Because that is basically what? Room temperature. Yeah, it's basically room temperature. So knowing these values of that, so if we were to figure that out based on Kw is equal to x squared, what is each one of those concentrations equal to? It says it on the paper. 1 times 10 to the negative 7 is what each of these is equal to. Because if we were to do Kw is equal to x squared, and we take the square root of 1 times 10 to the negative 14, we would get 1 times 10 to the negative 7 for each one of those in a solution. Okay? So that is when you are basic, not when you're basic, when you're neutral, okay? So when you're neutral, they're equal to each other, okay? If you have an acidic solution, then you have higher hydrogen concentration. If you have a basic solution, then you have a higher hydroxide concentration. If you know one, you can get to the other one based on that constant of 1 times 10 to the negative 14, okay? Because no matter what, because we're dealing with acids and bases that are in water, no matter what, the Kw has got to be equal to 1 times 10 to the negative 14. So if you adjust and make one higher, then you're going to make the other one lower so that it can still equal out to that 1 times 10 to the negative 14. Okay? Any questions on that? Does that make sense? Okay. And this, because these are like this, is why we're able to do pH calculations. Okay? So here we have an example, and they are giving us predict whether the reaction is exothermic or endothermic. So at 60 degrees, the value of Kw is 1 times 10 to the negative 13. So is this process endothermic or exothermic? Well, I mean, it says it's endothermic, but why is it endothermic? When we heated it up, what happened to our Kw value? It got larger, right? And so if it got larger, which way did this thing shift? Right. Shifted this way. So if it shifted that way and we heated it, that means it's an endothermic reaction. Okay? So now it says to calculate the concentration of both of those at that temperature. So we're going to do Kw is equal to H plus and OH minus, which would end up being x squared, right? So we set that equal to this number up here so that we get the hydrogen concentration is equal to the hydroxide concentration, which would be equal to 3 times 10 to the negative 7 molar. Okay? So one of the things that I saw that, y'all did it not quite as bad on the test because it caught you on the quiz, is when you solve for x, you still have to label it. Okay? Don't just solve for x and leave that as your answer. Label it. So like I didn't just say x was equal to, I said that the concentrations were equal to each other, which is the final answer. Okay? Make sure you label things when they're asking you a question. Also, make sure when they ask you a question that you actually answer it, like state the answer, okay? And always, if it says justify, then make sure you don't just write the answer, you justify as well. Don't just say it's endothermic, but you have to say why, okay? So that's still catching a few people. Like they answered the reason. Like on one of the things, they said they listed the explanation, but then they didn't state the reason or the answer to that question. So I think if y'all did that, I said make sure you answer the question on your notes to your test. Which, by the way, if you're someone who knows you need to retest, I will be available in the morning for tutorials, so you can come in and look at the test along with the key. I shouldn't have any pre-AP kids in here tomorrow because they had their test today, so they don't have any questions for me tomorrow morning. So it should be completely open to AP kids only, so you don't have to fight for the attention, so to speak. Yeah. And if you didn't fail your test and you want to come in and look at your test, that's perfectly fine too. Okay. Okay, so here, that brings us to the pH scale. The pH scale, of course, you get those on your formula chart. The pH is equal to the negative log of the hydrogen concentration, POH, negative log of the hydroxide, and then together they equal 14. So if you have one, you can solve for any of those, okay? I would like to remind you of if you have pH and you need to get to the hydrogen concentration, you take the antilog of that. So it would look like this. If I wanted the hydrogen concentration, it's equal to 10 raised to the negative pH. So if I gave you that the pH of the solution was 4.2, you could figure out what the hydrogen concentration was. And of course, to get the hydroxide concentration, it's 10 raised to the negative POH. You must put the negative pH and the negative POH in there. Why? Why is it 10 raised to the negative pH and not just 10 to the pH? Because it's a negative log. So don't forget, because if you just do 10 to the regular pH without the negative sign, it's going to give you a funky number. Okay? So sig figs, significant figures for pH. I don't know if you remember this from Chem 1, but they're basically the number of decimal points in your pH is how many significant figures you need. Okay? So if I gave you a pH of 4.2, how many significant figures would you report your concentration in? 1. It's just that you're just looking at the decimal places. Okay? So if I gave you a pH of 4.22, then you would give me a concentration in 2 significant figures. Because that first number is basically what the log scale. Okay? So the first number does not count in the pH, I mean in the sig figs, just the decimal places. It's confusing, I know, but that's the way that works. The number of sig figs should match your number of decimal places in the pH. So like sig figs for concentration should match your decimal places in pH. Do y'all remember that from Chem 1? Pre-AP? Yeah. Do my juniors remember it? And my senior? Yeah. Yeah. Okay. So here we're going to calculate either the hydrogen or hydroxide from the information given below and state whether that solution is neutral, acidic, or basic. Okay? So there's actually 2 ways you can do this. The quickest way, since they're giving you the hydroxide or hydrogen concentration, is remember that Kw is equal to H plus times hydroxide. So in this case, I would say the hydrogen concentration is going to be equal to Kw over hydroxide. So 1 times 10 to the negative 14 over 1 times 10 to the negative 5. And I get 1 times 10 to the negative 9. But we could determine whether this was basic or acidic before we ever went there by looking at this number. Is that number greater than 1 times 10 to the negative 7?
No.
Yes. So this would be basic. Yeah, negative 5 is greater than negative 7, right? Yes, sir.
Kind of like whenever I kind of looked ahead, I looked at like one of the pH questions, and all their exponents for 10 always add up to 14. Like, that could be a pattern.
Yeah, it should be a pattern. Just be careful when you're dealing with numbers other than 1 that it does. But yeah, they should absolutely.
Where does 1 come from, the negative 14 come from?
As the auto-ionization constant of water. And all of these solutions are in water, so they have to equal that overall. Yeah. Okay, so now the next one, what is that? Do we even need to do the math? That is neutral, right? So it's good to know that the hydrogen and hydroxide are that number when they're neutral, so they don't have to worry about calculating it. And then the last one is 10 molar. Well, 10 molar is really strong. So the hydroxide concentration is going to be 1 times 10 to the negative 14 over 10. So we're going to have 1 times 10 to the negative 15. So in that case, it's not going to add up to 14, but it is incredibly acidic. It's very strong. 10 molar is really, really strong acid. Concentrated hydrochloric acid is 12 molar. And so if you were to do a pH, you'd get pretty much negative pH values because it's so acidic. Because occasionally you can plug that in and get a negative pH number. But we just say it's pH of 0. Okay? How do I do what?
How'd you get basic or acidic?
I looked at the concentration of the hydrogen, honestly. Or, yeah. So, because at neutral, the hydrogen is 1 times 10 to the negative 7. So if it's basic, you're going to have a much smaller number than that. So in this case, we had negative 9. So it's basic. But I could also look at this negative 5 and see that that is greater than negative 7 and know that it's basic that way as well. And then on the last one, this is way, way greater than 1 times 10 to the negative 7, so it's definitely acidic. Okay? We already did that one. Did I put that in there twice? I did for some reason. Okay, so on this one, you can calculate the pH and pOH for each of the following solutions. That should be pretty straightforward because it's given us the concentration. So the first one is a hydroxide. So the easiest thing to do, you're going to actually approach this one of two ways. You could calculate really quickly what the hydrogen concentration is, or you could take the negative log of that. That gives you a pOH and subtract from 14. Either way you want to do that. Which way would you prefer? So, yeah, so we're going to take the negative log. Whoops, sorry, I didn't say I wanted to write. We're going to take the negative log of the hydroxide concentration. So we're going to plug that number in. And when we do, that will be the pOH is equal to 3. So then that means 14 minus 3, the pH is 11. Okay? So if the pH is 11, it doesn't say to do this, but this solution is basic.
How do you do the other one?
I would have taken the 1 times 10 to the negative 14, divide by 1 times 10 to the negative 3, would have gotten 1 times 10 to the negative 11, and then taken the negative log of that directly. The first way we did it's faster. Yeah. Okay? And then to get the pH of the next one, we're literally just going to take the negative log of the H plus, which is that number there, and get pH is equal to, you should get 0. And then the pOH is 14. Definitely acidic. Okay? Yes, ma'am?
So if the pH is greater than the pOH is basic?
No. Yeah. So yes, but usually when we're looking at things, we're looking at the pH scale, and we're usually just calculating the pH. So a pH of 7, less than 7 is acidic. A pH of greater than 7 is basic, and if it's 7 exactly, it's neutral.
It's like the opposite of what you think it'd be.
Yeah. So, yeah. I mean, if you want to think of it in terms of pOH, the pOH has to be less than 7 for it to be basic. Yeah. But normally when we determine acidic or basic, we are normally looking at the pH. Yeah. But you do need to know how to do this, because when we do KBs of a weak base and they ask you to solve for pH, one of the common mistakes is you get your concentration of hydroxide and then you take the negative log and then you think that's your answer, and you forget to take that one little extra step of subtracting it from 14 to get to pH. So make sure you don't do that. Okay? Because they will normally not ask you for a pOH on a Ka, Kb problem. They want you to tell them the pH. Okay? And then especially when we get to buffers, I'm going to warn you now, buffers stink. They're tough. They're tough. Yeah. Yeah. Okay. This is usually considered one of the equilibrium, but acid-base equilibrium is usually considered one of the toughest units in AP. Yeah. Between equilibrium, yeah, between last equilibrium and this one, February, is not really much fun. Okay, so calculating the pH. Calculate the pOH, the H plus, and the OH minus for the sample of pH of a human blood is known to be 7.41. So it's slightly what? Slightly basic. So you're all slightly basic. Okay. We could put that on a shirt. That's not. Oh, speaking of shirts, let's bring in our design ideas for not Monday, Tuesday, so we can get that process rolling. Because once we pick a design, it takes me a while to design it in custom ink. So let's come up with some ideas. But I like that. We're all slightly basic. Yeah, I do like that. Okay, so what did I tell you about pH? How can I get to the hydroxide concentration? I mean the hydrogen concentration. So we're going to take that H plus concentration, and we're going to say 10 raised to the negative 7.41. Because it gave us the pH, so the hydrogen concentration, we're just taking the antilog of what we took the log of to get. So that gives us the hydrogen concentration. Everybody do that in your calculator, make sure you get it right. 3, and I need how many significant figures here? 2, because I have 2 decimal places, so it'd be 3.9 times 10 to the negative 8. That's good. We got the answer they gave us on the paper. Okay. So we could go ahead and we could also go ahead and get our pOH here, right? What's our pOH going to be? 6.59. How'd you get that, Rohan? Very good. Okay. And so now to get our hydroxide concentration, we're going to do 10 raised to the negative 6.59. And so that, again, we need just 2 significant figures, right? So that should be 2.6 times 10 to the negative 7 molar. Conversely, you could have done it this way, just to show you, because there's more than one way to get to Dallas from here. I used to say there's more than one way to skin a cat, but people were offended. So you could have also gotten hydroxide concentration this way, 1 times 10 to the negative 14, divided by 3.9, times 10 to the negative 8. You would have gotten that same thing. So you could also do it that way. Okay? Any questions on that so far? This is the easy stuff, by the way. Okay? So, pH of strong acids. To get the pH of strong acids, we literally just take the negative log of their concentration. The only thing you can do that for is strong acids and strong bases. You cannot do it for weak. Weak are going to be a big process, including rice tables. Okay? Okay? So, I'm going to take the negative log of 0.1 molar. And I'm going to get 1.0. Negative log of 1 times 10 to the negative 10 is going to be equal to what? Do I even need to use my calculator to do that? It's 10. This is what you need to brush up on before you take the test in here, and definitely before the AP exam. You need to brush up on your log rules, okay? Because there will be pHs, and they're wanting you to calculate and estimate pHs on the multiple choice portion, and you don't have a calculator for that, okay? So it's actually pretty easy if it's a 1, okay? Like 1 times 10 to the negative 1 is going to be a pH of 1. 1 times 10 to the negative 2 is going to be a pH of 2. Times 10 to the negative 3, you get the point? Now, if you start doing decimals, then it depends on how close you are to that next negative number. So if I have 1.7 times 10 to the negative 1, it's still going to be 1 point something. But let's say I have 8.9 times 10 to the negative 1. That's going to be a little closer to 2 because you're fixing to get into that range where you would bump up to 1 times 10 to the negative 2 because it's getting large. You see what I'm saying? Like you have to look at, yeah. So you need to probably spend some time because they don't teach all that in math, the log rules?
Yeah, they do.
We have calculators.
In pre-calc.
We know how to like do like log times log is really like log
It's like
plus
a-
log.
Oh, you won't have to do that. You won't have you won't have to do math with logs, but you need to be able to estimate. Okay, so if they're not teaching how to estimate logs based on math, let me see what I can find. I'll see if I can find something on that. Okay, but that makes a difference. If it's a 1 times 10 to the negative whatever, it's easy because it's just the exponent. But when you start getting numbers with decimals in there, then you got to say, well, is that really closer to 1 times 10 to the negative 1, or is it closer to 1 times 10 to the negative 2? And then look at it that way. But there will be times where you have to estimate pHs without a calculator, for sure. Okay. Well, God, maybe I need to tell him to teach all that math. Okay, so calculate the pH of a 5 times 10 to the negative 2 molar solution of sodium hydroxide. Okay, so if I take the negative log of that number, I don't have pH, do I? No, I have POH, so I need to circle that right away when you see that so you don't accidentally just take the negative log and say I'm done with the problem. So I am going to take the negative log of 5.0 times 10 to the negative 2, and that's going to be my POH, right? And so I would get 1.3, and then my pH would be 14 minus 1.3, so it's 12.7. Just make sure you make little notes like that to yourself, because on a test, especially when you're working quickly, you might just take a negative log of that, and that answer's probably on there, and you go, oh, my answer's on there, and then you circle it, when in fact you needed to subtract from 14.
Does it have 2 decimal places?
It only has 1 decimal place. This has 2 significant figures, so I should have had a 0 and a 0. There you go. Sorry, my fault. So it should have 2 decimal places. Sometimes I forget to include the zeros. Okay, so now we're getting to the good stuff. Calculating pHs of weak acid solutions. Okay, we're going to have equilibrium, and we're going to have rice tables again. And I know you love rice tables. Okay, so here is an example. If I was to calculate the pH of a 1 times 10 to the negative 4th solution of acetic acid, and I'm giving you the Ka of acetic acid, you will usually be given that unless they're giving you information about concentration and want you to solve for Ka. It's not a bad idea. You'll see the Ka of acetic acid a ton. It's one of their favorite weak acids to use, so most likely you'll have that memorized by the time we're done with this unit, just because we see it all the time. Okay, so same process. We've already done rice tables. Initially, we have a concentration of acetic acid, and then 0 of the 2 ions, and then we do minus x, plus x, and plus x. So then we plug it in, and we know how to do this. Okay, here's where this is where that neglecting x comes in handy. Almost every problem on the AP exam, if you're having to work an acid base, almost every time you'll be able to neglect x. But don't forget to go back and check, was I within the 5% rule? Okay.
Do you have to work the whole problem again?
You could, I mean, if you were writing it on paper and you said neglect X and then you said check within 5%, assumption is valid. But if you found that the assumption was not valid, you would say assumption not valid and then just work it again. Don't cross out your work. Oh, that's the sidebar. On the AP exam, if you make a mistake, same thing in here. If you make a mistake, please don't waste time erasing. Just mark it out and move on. Do not erase, okay? But if you don't want them to grade it, draw a line through it. They will not, and I don't know if you've noticed that. There's been a couple of times where someone had the right answer, but they crossed it out. If you cross it out, I don't grade it. Okay? If you cross it out, they won't grade it. You could say, I think the College Board, stinks. You cross it out. They can't do anything about it. You can't grade it. Okay? But if you cross it out, know that if you had it right and you cross it out, they're not going to give you the credit. Okay? I'm just saying. Okay? So on a test, because I've seen some people like taking the time to erase. Don't take the time to erase. Make a line through it and move on. Taking time to erase takes time, and as you know, where time is an issue in here. Okay. So we already talked about neglecting X. We talked about that in KSP. So we don't have to go through neglecting X because we already know how to do that. So they're just taking you through this example with neglecting X. Because some people don't introduce neglecting X until acid-base, but I introduced it sooner. And then this is just like a guideline of how to do this. Okay? And calculating the acid-base equilibrium is not what kids find difficult because it's pretty much straightforward like the other stuff. It's when we get to buffers, which is going to be next week. Okay? All right, so here we have the pH of the hypochlorite ion, and it gives us some information. That is not the one I wanted to work. That's just not, because I don't have that one in my notes. Where'd that come from? Oh, just kidding, I did. I just turned the page too soon. Okay, I'm going to give a new page because I can't fit it all in there. So here we go. Y'all ready? So we're going to start with our rice table. So we start out with 0.1, and then we have 0 and 0, and then minus x plus x plus x. So at equilibrium, we have 0.1, 0, 0, minus x, and x. They gave us a Ka value of 3.5 times 10 to the negative 8. So that's going to be equal to so we are going to assume x is negligible. So then it becomes 3.5 times 10 to the negative 8 equals x squared over 0.100. So now the math becomes much easier. And so x squared is going to be equal to 3.5 times 10 to the negative 9. So then x is equal to 5.9 times 10 to the negative 5th, and we could say that that was equal to the hydrogen concentration. So then we would say pH equals to negative log of 5.9 times 10 to the negative 5. So we get a pH is equal to 4.23. Actually, that's 3 decimal places to begin with, so we needed that one.
What do you compare x to see if it's negligible?
I'm sorry, what?
What do you compare x to see if it's
The concentration. So when we got x was equal to 5 times 10 to the, basically 6 times 10 to the negative fifth. That's way less than 5% of 0.1. You're looking at the original concentration, because if we were to put in our calculator 0.1 minus 5 times 0.9 times 10 to the negative fifth, what would we write down on our calculator based on significant figures? We would write back down 0.100, because it's not even showing up until like the 6th place, so it wouldn't make a difference in our calculation. Does that make sense?
Yeah.
So like the concentration of the HOCl is not going to change by hardly anything. And so we say, yeah, it's, and then, that, you know, valid assumption, you could write that. It's not always necessary to write valid assumption, but you should check it, because if it wasn't a valid assumption, so if you have a really, really small concentration of your acid, then it might be, but 0.1 is a relatively strong concentration for weak acids and weak bases. Okay? All right, so I would like, what time is it? I would like y'all to work the next one. Actually, no, I would not, because that's a mixture of acids, and y'all won't know how to do that. Never mind, I'll work the next one. What do you, where are you saying no reaction?
The worksheets.
Oh, never mind. Okay, sorry. I was like, okay, never mind. Okay, so this one says calculate the pH of a solution that contains 1 molar of HCN and 5 molar of HNO2, and it lists the Ka values. And then it says also calculate the concentration of the cyanide ion at equilibrium. Okay, so when you have a mixture of acids, especially with both weak acids, the only one that is going to contribute any kind of appreciable amount of hydrogen is the larger or the strongest one, so the one with the largest Ka. So then you're going to determine the pH based on that. So based on this one, the nitric acid is our one that we're going to do the pH based on that. Okay? So I'm going to do a new paper again. So HNO2.
Miss Parker?
Hello? Okay, H plus. Plus NO2 minus. So we're going to have 5 molar, which is a relatively, that's a really large concentration. 0, 0, minus X. So remember when we were doing KSP for, we didn't even have to really keep doing the rise tables. We just started doing like 4x cubed. So at some point you can do that. You could just say 4 times 10 to the negative 4th. Let's just redo that. That looks terrible. It's going to be equal to x squared over 5. So we do the math and we get x is equal to the hydrogen concentration, which is going to be equal to, where did I write that down? 0.0447. Okay? So then we take the negative log of that. So, and we get a pH of 1.35.
Did you just assume X is negligible and not write it down?
Yeah. Assume negligible. You can say assume negligible, or you can just say neglect. Either way, you just have to show them on paper that you're neglecting X. You just didn't like forget about it. So you need to actually circle it. Usually I circle it and say neglect. So then our pH is 1.35. So this is what I was talking about yesterday. Don't confuse concentration with strength of acid, because even though this is a weak acid, a pH of 1.35 is still really acidic. Okay, so that's what that was talking about yesterday. So the second part of that is what is the concentration of the CN. So we would do Ka. Now if we were going to do that one, we would say H plus CN minus over HCN, right? Because we're looking for the CN minus. So we can solve for that because we have the Ka for the HCN. 6.2 times 10 to the negative 10 is equal to a hydrogen concentration of 0.0447. Why did I use that number? Because even though that was coming from the other one, it's going to contribute the only negligible amount of hydrogen. So we would use that even though it's coming from the other acid. We're solving for the Cn minus, and then it gave us a concentration of 1 molar for the HCN. So we do our math, our wonderful basic algebra 1 skills, and we would get 1.4 times 10 to the negative 8 molar. Do you understand why I did what I did? I will not have time to do percent dissociation, so we'll pick that up tomorrow. Yeah, I said Monday, but I forgot we're not here.